Now it's time for another sorting algorithm called bucket sort. Are you surprised at how many sorting algorithms there are? You should be, because there's a lot more sorting algorithms that we're not even going to cover. But bucket sort is definitely worth covering because it's unique in that actually it can run in big O of n time, even in the worst case. So it's super efficient. So why did we even bother learning the other algorithms that run in, let's say, n log n time? Well, that's the downside of bucket sort. It's very rare that you're able to use bucket sort. It's sort of a forbidden technique, which very rarely gets to be used. And that's because there needs to be certain constraints for the problem. In this case, the constraint is on the specific values that we are sorting. We're only allowed to use bucket sort if we're guaranteed that all the values that we're sorting fit within a finite range. So in this case, the only values we have are 0, 1, and 2. So we can say that the range of values is in between 0 and 2. Now, typically when you have an array of integers, usually the integer is bounded, like it might be a 32-bit integer or a 64-bit integer, and therefore we would have a range, right, like -2 to the power of 32 approximately, all the way to 2 to the power of 32 positive approximately. So we could say that that's our range, but that's a really, really big range, and that usually doesn't qualify for bucket sort. We're talking about generally smaller ranges, but in this case, we have a very small range, 0 to 2. I mean, you could have a lot bigger, 0 to 100, or maybe even 1,000, or 10,000, or 100,000, right? Like that's still relatively small. Back to our example. We have this constraint, so we can use bucket sort. So what are we going to do? Well, for every single value in our range, in this case we have a 0, a 1, and a 2, we're going to create a bucket for every single value. That's where the name bucket sort comes from. So for 0, we're going to have a bucket. For 1, we're going to have a bucket. And for 2, we're going to have a bucket. So I have an array of 3 values. This is where each of our buckets is going to go. So each of our buckets is basically a value itself. So for this array, we have indexes 0, 1, and 2. So conveniently for us in this case, the 0 is going to map to the 0 index, 1 is going to map to the 1 index, and 2 is going to map to the 2. It's not necessarily always going to be the case like this. For example, instead of having a 2 here, we could have had, let's say, a 4. In that case, we would just, arbitrarily put the 4 in this spot. The point is, for each of these values, we have it mapped to a position, and what this position is going to represent is the number of zeros that we have. So what we're going to do here is go through this array, count how many zeros we have, and then put that count over here. So we know we have 2 zeros, so 2 would go over here. Here we're going to put how many ones are in the input array. We just have a single one, so we're going to put 1 here. How many 2s are in the array? We have 1, 2, 3, so we're going to put a 3 over here. Now, what would be the time complexity of counting all of these? You might think we have to pass through the input 3 times, 1 for each of our buckets, but we actually don't. Let me just quickly show you how we would actually go about counting these. It's mostly straightforward. We would have an index, right, like I, starting at the beginning of the array. And actually just jumping into the code really quickly, assuming we're given an array like this, which, looks exactly as our example, and we have our counts, we're going to have an I pointer going from the beginning of the array all the way to the end. And what we're going to do is take this value 2. Well, first let's talk about how we're going to initialize our counts. Initially, we're going to say we have 0 zeros, we have 0 1s, and we have 0 2s. But as we iterate, we're going to get to the first value, we have a 2. So what we want to do is increment our number of 2s. We can do that by going to counts at index 2 and incrementing it by 1, because we know that 2 maps to the index 2. That's convenient for us. It might not necessarily be the case, but we could have some kind of mapping. So we can increment this by 1. And we're going to continue to do that. We're going to go here. We're going to end up incrementing our number of 1s. We're going to go here. We're going to increment our number of 2s again. We have 2 2s. We're going to go here. We have 1 0. Now we have 2 zeros. So increment the number of zeros to 2. And then we have our last value, which is a 2. So we increment the number of 2s to 3. So now just cleaning this up a little bit. After counting, we know we have 2 zeros, 1 1, and 3 2s. Now it's time for the second portion of the algorithm where we actually sort the array. So the reason we counted each of these values is because we know when we take this array and we sort it, of course the zeros are going to go at the beginning, then the ones, and then the twos are going to go at the end. We know the output is going to look something like this. So if we could just know how many zeros to put at the beginning, then how many ones to put, and then how many twos to put, and of course, maybe we would have some threes as well and have some fours, but in this case we don't. But if we can do that, then we can fill this in without having to swap these values around. Every sorting algorithm we looked at so far would swap values. We have a 0, we know that's going to go at the beginning, so we swap it with the beginning. But bucket sort does not do that at all. By the time we get to this point where we have counted all of the values, we don't even need the input values at all. We don't even care what these are anymore. We're just going to start overwriting them, and we're going to do that with a couple loops. So our outer loop is going to have a variable called n, which is going to iterate through every position in counts. So we're going to iterate from 0 to counts.length. So we're going to go from here to here to here. By the way, this is just pseudocode. It's not necessarily syntactically correct, but this is the main logic that any program in any language would follow. So we have n. And then in the inner loop, we're going to have a second pointer. Let's call it j, which you can see j is not actually being used anywhere, but we're just using this pointer to iterate this many times. So let's forget about j. Let's just see how many times are we iterating. Well, 0 to counts of n. So basically what I'm saying here is we're going to iterate this many times. At this point, our n pointer is here, so we're going to iterate 2 times. Now, what exactly are we going to do? We can see we have a third pointer, I. This is important because I is going to tell us where to fill in the value. Initially, I is going to be at 0. Of course, we would want to fill in starting from the beginning. So we're going to fill this position with whatever n happens to be. We know n is the value, 0 is the value, so we're going to put 0 over here. And how many times are we going to iterate over this loop? Well, whatever counts of n is, 2 times. I hope it's starting to make sense now. We have 2 zeros, so we're going to put 2 zeros at the beginning of our array. So we're going to increment I now to be over here. We're going to put a 0 over here. And then our inner loop is going to finish executing. And then we're going to go back to the outer loop. Now our n is going to be incremented. Our n is going to go over here now. So now how many times are we going to execute the inner loop? Well, n is at 1. How many ones did we have? We only had a single one. So now with our I pointer over here, we're going to fill in a 1, and then we're going to increment our I to be at the next position. And this loop only executed a single time, and then our n is shifted here. So we're going to put a 2 over here. We're going to increment our I. We're going to put a 2 over here. We're going to increment our I, and we're going to put a 2 over here. We just ran that 3 times. So our inner loop is finished executing. Now we're going to go to the outer loop and end up shifting our n one more time. Now it's out of bounds. That's how you know we're done with the outer loop. We're done with the algorithm. Our array is sorted and we can return it. So now the question is, why is this algorithm big O of n? Because don't we have nested loops over here? Well, as I just showed you, this nested loop portion, how many times is this nested loop portion actually going to run? Just because we have nested loops does not mean the time complexity is n squared. We know that this I pointer is going to be incremented every time the code actually runs and evaluates. And as I just showed you, our I pointer is going to start at the beginning and then keep being incremented until it goes out of bounds. How could that possibly be n squared? Just because we have nested loops does not mean it's n squared. Because the first time the loop runs, it ran twice. Then the next time it ran once. And the next time it ran 3 times. All of those are always going to total up to be n, because of course we're only going to have n values these are just the counts, and then we're going to put the values into the array, which of course is of size n. So what I'm saying is this nested portion is big O of n time complexity. Of course, we did have to iterate through the input one time before that over here, and the time complexity for that was also big O of n. Well, adding these together would make the time complexity big O of 2 times n, which, we know reduces to be O of n because we don't care about constants. So the overall time complexity is big O of n. In this case, though, we are using a bit of extra memory. We're using an array, but what's the size of this array going to be? It's going to be whatever the range of values happens to be. The possible range of values. And we know, in this case, it's from 0 to 2, but it could be, from some constants n to m, something like that. And as long as it's some fixed size that isn't like insanely large, we assume that this is a constant. So therefore the extra memory we're allocating, in this case, it's big O of 3, but it's going to be some constant c. And we know constants reduce to big O of 1 space complexity. But I do want to mention that this is sort of a forbidden jutsu. It's very rare that you're going to actually use bucket sort. The only time you're probably going to end up using it is in an interview, to be honest. But there definitely are some practical applications, and maybe you'll come across them at some point in your career. Now, the last question for us to answer, is bucket sort a stable algorithm? Well, the answer is pretty short, no, and I think in this case it's actually pretty clear why. When we overwrite the array, we're not even caring about, which 2 came first, because we just counted that there were 3 2s and they're all going to go in the last 3 positions. We don't care which one goes where. In fact, we're not even swapping the values anyway. We're just overwriting them. So it doesn't preserve the relative order at all. So bucket sort is definitely not a stable sorting algorithm. But if we wanted to, technically we could make bucket sort a stable sorting algorithm, because for example, as we count the 2s, we could preserve that somehow. For example, if this was actually a linked list instead of an array, as we count the 2s, instead of just counting them, we could have actually taken each 2 and added it to a linked list. So we would have a series of 2s like this, where this one would have been the first one, this one would have been the second, this one would have been the last. And then when we finally build the result, we would have put them together something like this. Now, this isn't super important to understand. I'm just mentioning it anyway. It's pretty rare that bucket sort is used on anything other than an array anyway. So now lastly, let's compare our sorting algorithms. So bucket sort, which is generally an unstable sorting algorithm, runs in the worst case in big O of n time, but it's a little bit misleading. Remember I said this is sort of a forbidden jutsu. Most likely you won't be able to run bucket sort on the input that you're given. But if you ever are given an input where bucket sort can be run, don't ever use any of these other algorithms because they're not going to be as efficient as bucket sort. If you are given an input where the values are within some specified range, always use bucket sort. Otherwise, if you're given just a general input, most likely you will end up using either merge sort or quick sort. I think merge sort is generally more common.